Alright, so 9.2 part 1. Yes, I am going to read this to you because whenever we tell you to read something, you guys don't end up reading it. So just some background information. Determining values of a particular function is usually an important part of any problem solution. However, the evaluation of most functions without technology is at best difficult if not impossible. So polynomials are an exception since computation of their values is essentially an arithmetic problem, correct? So if a function can be approximated by a polynomial, like we did successfully in section 1 when we approximated that this function with the power series 1 plus x squared plus x cubed plus x to the fourth on the interval of convergence negative 1x, negative 1, 1, and the difference between the function values and the power series approximation is small, i.e. the error between the two was small. So since we were able to do this, then we can use the values of the polynomial to approximate a value of the function at a given value of x within the interval of convergence. So we can use the values of the polynomial to approximate a value of the function within the interval of convergence. So the important idea is we can use the polynomial to approximate the function for a given value of x within the interval of convergence. This is how we do this. So approximation at a point and over an interval. So and. Don't forget that. It's not or, it's and. So we can approximate at a point and it must be over an interval. So suppose we're interested in approximating the cosine function. We might need to make a quick estimate and may not have a calculator handy. If we know the power series for cosine, we can do such an estimate. Okay? So here is a second degree polynomial that is a reasonable approximation for cosine of x over the interval negative pi over 2 to pi over 2. So p of x is equal to 1 minus x squared over 2. So let's plot these two together to see how good of an approximation it is. So we're basically telling you that we can have a power series that looks like this for our function that looks like this. Okay? So if you were to graph this in the calculator, you would notice that the cosine function is up here. Okay? That's our cosine function, and then our power series is this one right here. So what does this tell us? So how do f of x and p of x compare on this interval? Cosine of x, which in this case is my f of x, and 1 minus x squared over 2, which in this case is called my p of x, are very close, except where at the end of the interval, close to pi over negative pi over 2 and pi over 2. Agree? That they're very, very close, except for at the ends they kind of start to diverge a little bit. So what we want to do is we want to fill in the table calculating the absolute value of the difference or the error between f of x and p of x at various points so that we can test this. Alright, so basically cosine of negative pi over 2, that's easy, 0. Cosine of negative pi over 3 is 0.5. Cosine of negative pi over 2 in the calculator is 0.7071. Cosine of negative pi over 6 is 0.8660. So I'm using approximations. Cosine of 0 is 1. And then pi over 4, should have started with pi over 6. I think that printed out wrong. Don't know. Sorry guys. That printed out wrong. That should have been pi over 6. Can you please change that? I don't know why that printed out like that. Alright, so at pi over 6, it's 0.8660, and then it just repeats. 0.7071, 0.5, and 0. Okay? And they're all positive. So now if we plug in those same numbers, so negative pi over 2 in for x, and yes, you can do this on the calculator along with me. I'm not going to do every single one because I'm going to have you guys finish this, but if you plug in negative pi over 2, you will get negative 0.2337. That's our approximation. You notice I'm taking 4 decimal places all the time because you want it to be pretty accurate. And then the next one, you plug in negative pi over 3, so 1 minus negative pi over 3 squared over 2, you get 0.4516, and so on and so on. Now down here, if you plug in 0, that one's easy, so 1 minus 0 is 1, and let you guys plug in the rest of these to see what you get. So here, we're calculating the error. And basically, the way you calculate the error is you take your f of x minus your p of x. So here's my f of x minus my p of x. So when I subtract these two, what do I get? I get 0.2. Did I make a mistake here? Was this supposed to be negative? Yeah. 0.2337. Okay? And then the next one is 0.0484. And as you go down here, the error is 0. Down here, once you subtract the two numbers, you should get 0.0031, and then 0.0156, and then 0.0484, and 0.2337. So what do you notice? Okay, I'll let you guys fill this in to figure out the numbers. I mean, now you can do it just mathematically. But where does the largest difference occur using the given set of x values? And you can see that the largest difference is going to be at negative pi over 2 and at x equals pi over 2. Where is the approximation the best? Obviously, at x equals 0. Alright, how does this compare to the graph on the previous page? The table of values are in agreement. Can you agree? It's obvious that it was diverging when you were getting closer to the interval of convergence, to the ends of it, and then in between it was almost perfect. So the table of values are in agreement with that observed in the graph. All right, how would you rate the polynomial p of x as an approximation f of x? Do you think it was a good approximation or a bad one? P of x is an excellent approximation. For the function cosine of x everywhere on the interval except where? Except near the end points x equals positive or negative pi over 2. So yeah, it's a pretty good approximation, except as you get closer to the endpoints within that interval. Okay, so this question should have said, how would you rate the polynomial as an approximation of f of x within the interval negative pi over 2, pi over 2. All right, how could you make the approximation of the polynomial p of x to f of x better? Obviously, when you noticed, what did we graph for p of x? We graphed just 1 over x squared plus 2. So we only graphed 2 terms, correct? So what do you think if we added more terms to this power series? It would obviously be an even better approximation. So how could I make it? Add more terms to p of x. Okay. Which brings us, I'm going to finish this page, and this is going to be our part 1 of our notes, okay? Which brings us to our Taylor polynomials. So we have already seen in our study of linearization technique, if you remember, you take a function and you try to basically line it up to find the tangent line. So L of x is equal to f of a plus the derivative of f times x minus a, that a tangent line at the point is the best linear approximation for the function at that point. That was what we did in derivatives, the derivatives section. So let's consider f of x equals cosine of x, and the power series at x equals 0, p equals 1 on the interval negative pi over 2 pi. So if I just graphed the first term, p equals 1, within this interval, what do you notice? At x equals 0, is that a good approximation? Yeah. So basically here what we just did is the horizontal line function p of x equals 1, i.e. f of 2 of x equals 1. It approximates the function f of x equals cosine of x perfectly, but not everywhere, right? Where does it approximate it perfectly? At x equals 0, which is what the question was asking about over here. So how is the approximation of p to f of x at x equals 0? Perfect. How is the approximation of p to f of x at x equals positive or negative pi over 2? What is the approximation? Not good at all. Okay? So in general, if a function f of x is differentiable at x equals a, then the tangent line approximation of f of x at x equals a is given by p of x equals f of a plus f prime of a times x minus a, which also happens to be the linearization equation. So nothing new, but now we are adding it to our power series approximation, which also happens to be the linearization equation, and we refer to this polynomial p of x as the Taylor polynomial of degree 1, or p1 of x. So basically p1 of a is just f of a, and p prime of a is just f prime of a. Okay? So basically the idea is this p1 of a is equal to f of a plus f prime of a times a minus a, which gives us f of a, because p1 of a is equal to f of a. And this is just referring back to it as a linearization equation, right? A minus a is what? 0 times this is 0. So we end up with p1 of a is equal to f of a. Okay? And then therefore P prime of the first term of A is equal to also F prime of A. Alright, as you might suspect by now, Taylor polynomials of higher degree, polynomials with lots more than one term, will produce better approximations of the target function at a given point. So if A at F is a function with n derivatives at x equals a, then the Taylor polynomial, or the Taylor series, of the degree n approximating the function f of x about x equals a is given by all of this. So I'm going to stop here. This is where we're going to start the next set of video notes. Alright, good luck.